Okay, all right. So today we have a lecture number 12. Or our focus will be on the advanced topics. So what we will cover in this lecture, we will cover some interesting advanced topic like hardware assisted security, container security, operating system hardening, zero trust models, root of trust, file system encryption, memory safety, secure operating system architectures, patch management, advanced resistant threat detection model, biometric security integration, and finally, our focus will be on the quantum resistant cryptography. First, we have to discuss here hardware assisted security. So, as we know, in the evolving landscape of cybersecurity, hardware assisted security has emerged as a critical line of defense for enhancing the security measures of operating systems. So this topic gonna leverage the intrinsic capabilities of hardware components to fortify software and data security. It's gonna address the vulnerabilities that software alone solution cannot effectively mitigate. So first of all, understanding the hardware-assisted security involves the integration of physical hardware features, especially designed to handle security processes alongside the operating systems. So this integration is important in creating a robust, secure security framework that can provide hardened barrier against various types of cyber threats, like, for example, exploit software vulnerabilities. So the key technology in hardware-assisted security uh, consists of two of the most prominent technology in the domains are first is Intel Software Guard extension and another is ARM Trust Zones. Both technologies provide unique approach to securing sensitive data and critical applications by facilitating secure computation in isolated environments. So first of all, if we're gonna discuss here, we have Intel Software Guard extension. This is a set of security related instruction codes which are built into the some Intel CPU. They allow applications to create protected enclaves which are secure areas of execution memory. The code and data loaded inside these enclaves are protected and cannot be accessed or modified by any other process, like process running at higher privilege levels, and SAGX is designed to be flexible, allowing software developers to partition their applications into multiple enclaves as needed, thereby enhancing security without compromising on performance. So this capability is practically useful for protecting data and the user, ensuring that sensitive information is only decrypted and processed within a secure environment that external entities cannot access. Second, we have here ARM Trust Zone. So this technology is a system-wide approach The security on ARM processors often found in mobile devices, embedded systems, and increasingly in larger computing systems. Trustzone introduces a secure mode at the hardware level, creating an environment that runs alongside operating systems in parallel with the normal operating mode. So this secure mode can operate independently of the operating system, providing a protected area for sensitive data and critical security functions. So we can say like that applications can leverage trust zones to perform confidential and cryptographic operations safe from exposures to high risk software environments. This dual environmental setup is important for tasks that require strong security measures such as mobile payment, secure boot, and device authentication. Application impact of hardware assisted security means like the application of hardware assisted security are vast and impactful by providing mechanisms for isolated execution technology like SGX and Trustzone play a critical role in enhancing data protection, particularly in the scenarios where sensitive data must be shielded from potentially compromised operating systems. For instance, in cloud computing environments, SGX enclaves can be used to secure cryptographic keys and personal data from other tenants of shared hardware, mitigating the risk of the side channel attacks. Moreover, the use of hardware assisted security in a consumer electronics such as smartphones and tablets has become increasingly important. ARM Trust Zone, for instance, is integral in securing mobile device payments and enforcing various digital rights management policies, ensuring that both financial transaction and digital contents are handled securely. So we can say like that as the threats become more sophisticated and pervasive, hardware assisted security offers a compelling layer of defense that complements software based security solutions. Intel's SGX and ARM's touchstones are at the forefront of this technology, providing essential tools for developers and organizations to protect sensitive data and ensure the integrity of their operations in a secure, isolated manner. As this technology evolves, it will continue to play a critical role in shaping the future of cybersecurity, addressing the emerging threats with a robust hardware-based security measures. Now we're going to discuss here container security in the modern era of software developments, containerizations technologies such as Docker and Kubernetes have revolutionized how applications are developed, deployed, and scales in the cloud environments. However, the dynamic and distributed nature of containers introduce a new security challenge that must be addressed to protect sensitive data and maintain system integrity. Ensuring the robust container security encompasses several key areas, including container isolation, secure architecture, and vulnerability management. So under a container security, the container security involves protecting the software containers that encapsulate applications code, dependencies, and their runtime environment. Unlike traditional monolithic applications or virtual machines, containers share the host system's kernel, which makes them lightweight but also introduce a potential security risk if not properly isolated and managed. Container isolation is one of the fundamental aspects of container security, is ensuring that containers are adequately isolated from one another and from the host system. Proper isolation helps prevent malicious processes within one container from affecting others or gaining unauthorized access to the host system. So this can be achieved through various mechanisms. Now we have to discuss here some features like name spaces, Linux namespaces are pivotal in providing the isolation needed for containers. They ensure that each container has its own isolated runtime environments, including its own network stack, process ID space, mount points, and inter-process communication resource. Another is C groups we call the control groups. So C group complement namespace for by limiting and isolating the resource usage like a CPU, memory, input, output, etc. of containers. This prevents any single container from exhausting the host resources and ensures consistent performance across all containers. And then we have to discuss here secure container architecture, a container deployments, scale architecture tools like Kubernetes play a critical role in managing the life cycle of containers. Secure architecture involves several practices like it's gonna provide like automated security policies, means implementing, enforcing security policies automatically across all containers to ensure compliance with the security standard. Other is a role-based access control, means configuring a role-based access control who can access the Kubernetes API and what actions they are permitted to perform, which gonna help to minimize the potential attack surface. Now we have another feature is a network policies. It means we can define network policies to control the traffic flow between containers, ensuring that one authorized containers can communicate with each other. And then we have to discuss vulnerability management within containerized applications. It means like vulnerability management is critical in maintaining the security of containerized applications. This consists of several steps. Let me explain these several steps. First is a regular scanning. Containers should be scanned regularly by finding the vulnerabilities using automated tools that can detect known security issues in the container image and their dependencies. Image signing and verification. Second one is means we have to ensure that only trusted containers are used in the environment by implementing image signing and verification process. And then we have a third one is page management, and we're gonna discuss in detail on page management in the next slide, but let me explain here. So keeping all container images up to date with the latest security patches is very important. So automated tools should be used to rebuild images and deploy containers whenever updates are available. So we're gonna say that the increasing reliance on containerization technologies demands robust security measures to protect against evolving threats by focusing on container isolation, secure architecture, and comprehensive vulnerability management. Organizations can safeguard their containerized applications effectively as technology evolves. So too must the approach to container security requiring ongoing attention to new vulnerabilities and continuous improvement of security practices. Addressing these challenges head on will enable businesses to leverage the full potential of containerizations while minimizing risk in their operational environment. Now we have to discuss here operating system hardening. So operating hardening is a critical component of system security that involves implementing a set of technologies and strategies designed to reduce vulnerabilities. This is a proactive process that gonna enhance the security posture of systems by minimizing attack surface and securing a system configurations. Effective operating system hardening not only protect individual computers but also fortifies the overall network security by reducing the chances of successful attack. So what are the key aspects of operating system hardening? The first key aspect is minimizing attack surface. The first step in operating system hardening is to reduce the attack surface by removing or disabling unnecessary services. And also we have to remove unnecessary applications and protocols which are not essential for systems operation. Each service running on operating system can potentially introduce vulnerabilities. So we have to minimize these components, limits the opportunities for malicious exploitations. So what measures we should take to reduce and mitigate those kind of risk? So first, we can uninstall unused software. So removing applications that are not necessary for our system's primary functions. And second is disabling unnecessary services. Means services that are not required for system operations should be turned off. For instance, if a server does not need to serve web pages like a HTTP service should be disabled. And then we have use a configuring security settings. Means a proper configuration of security settings is very important. Why? Because we can protect the operating systems. So this involves adjusting a default security settings according to the best practices tailored to the specific environment and needs. So what are the key configurations that we have to discuss here? First, we have to strengthen user authentication. Means we have to implement strong password policies, enforcing multi-factor authentication, and reducing the number of privileged accounts. Second is we applying the principle of least privilege. It means ensuring the accounts and processes operates using the minimal level of rights necessary to perform their functions. And then third is configuring firewalls and intrusion detection systems. Means properly setting up firewalls to block unnecessary inbound and outbound traffic and deploying intrusion detection systems to monitor and respond to the suspicious activities. Third is a regular updates and patch management, keeping the operating system and all installed software up to date is a very important in operating system hardening. Software vendors frequently release patches to known vulnerabilities, and applying these updates promptly can protect systems from attacks that exploit these vulnerabilities. And then fourth is effective page management involves particularly updating operating system applications, automating updates that can ensure they are applied as soon as they become available. And we can also use vulnerability scanning and remediations process. And also we can use a secure network configuration. It means configuring a network settings securely further gonna enhance operating system hardening for protecting data as it moves in and out of system. So it consists of first one enabling a secure protocols. So it means we're gonna replace protocols that do not support encryption, such as FTP and HTTP. So we can replace FTP and HTTP with a secure alternatives, means new variants that gonna provide security like SFTP and HTTPS. And also we can provide a segmenting networks, means dividing networks into smaller parts. Why? Because it gonna helps to control traffic flow and gonna limit the spread of any potential intrusion. And also we gonna apply continuous monitoring auditing. So continuously monitoring the system for any signs of security breach and regular auditing the system configuration security measures are essential practices in maintaining and hardening environment. So what we will achieve? So it gonna ensures that security breaches are detected and responded to promptly, and also utilizing monitoring tools that provide a real-time alerts on suspicious activities. Compliance with the security policy is maintained. It means we can also apply regular audits that gonna help ensure that the hardening measures are consistently applied and remain effective over time. So let me conclude about this operating system hardening is ongoing a process that requires the diligence, regular maintenance, and a proactive approach to security. By implementing these hardening techniques, organizations can significantly enhance the resilience of their systems against cyber threats, thereby protecting sensitive information and maintaining the integrity of their IT environments. This foundational security strategy is essential for any organization looking to strengthen its defensive posture in the face of increasingly sophisticated cyber attacks. Now we have another topic here, new topic, the zero trust security models. It's gonna represent a fundamental shift in the approach to securing information system, moving away from traditional perimeter-based defenses towards a more comprehensive adaptive security framework. This model operates under the principle that trust should never be assumed, regardless of origins or nature of network traffic. By implementing zero trust principles, operating systems are configured to scrutinize every request and interaction that gonna ensure that every access attempt is explicitly verified before permission is granted. So understanding a zero trust security model, the zero trust security is protected on the notion that the threats can originate from anywhere. So we can assume the threats can come from anywhere, both outside and inside traditional network boundaries, and thus every request for access to resources must be securely validated. This approach requires strict identity verification, device security checks, and least privileged access controls to minimize the potential attack surface and reduce the risk of data breach. So let me understand thoroughly the key components of zero trust in operating system. First is a continuous verification. The core of zero trust model is that the trust is never implicit and must be continuously verified. In the context of operating system, this means implementing robust authentication mechanisms that can verify the identity and security posture of users and their devices every time they request access to resources. Multi-factor authentication, biometric data, and behavioral analytics are often employed to strengthen this process. A second component is least privilege access. So this principle involves restricting users and process access rights to the bare minimum required to perform their duties. In operating system, this means tightly controlling which files, settings, applications, and system functions each user to process can access. And also we can imply role-based access control and just-in-time privilege escalation can help manage these permissions dynamically and securely. Third component is a micro-segmentation. In a zero-trust framework, micro-segmentation refers to the practice of dividing security perimeters into small zones to maintain separate access for separate parts of networks. On operating system levels, this might mean isolating sensitive applications and data in a secure containers or using virtualization technologies to segment different processes, thereby limiting the potential damage from breach or any kind of possible threat. So the fourth component is end-to-end encryptions to protect data integrity and confidentially zero trust models mandate that data should be encrypted both at rest and in transit. This ensures that any data handled by operating systems remains secure regardless of their network's security status. Fifth component is a real-time threat detection and response. So the zero trust models rely on advanced monitoring and analytics to detect anomaly that could indicate a security threat. Operating system must be equipped with the tools to continuously analyze and log activities, employing artificial intelligence and machine learning algorithms to detect patterns that deviate from norm. Automatic response mechanisms are also crucial to contain and mitigate threat promptly. And also, fifth is like implementing zero trust in operating system, adopting a zero trust model within operating system environments require comprehensive planning, integration of various security technologies, and we can also conduct thorough audits of existing security protocols and system configuration. And we can also identify sensitive data, and also we can do system components that require enhanced protections. We can deploy the advanced authentication methods and enforce encryption standards, regularly update and patch operating system. And also we can protect against vulnerabilities, and we can also educate users on security best practices and importance of compliance with the new security model. So I can say here implementation of zero trust security models in operating system gonna represent a proactive and dynamic approach to defending against the evolving landscape of cyber threats. By assuming that there is no implicit trust and that every request or interaction must be verified, organizations can significantly enhance their security posture as cyber threats become more and more sophisticated and pervasive. The principles of zero trust provide a robust framework for securing critical system resources and sensitive data, ensuring that security measures are as resilient as the system they protect. So these techniques and components, if we really apply, then we can make sure that we can maintain the zero trust security. Zero trust security means there is no any kind of threat we have. Now we have another topic is a root of trust. So this concept of root of trust is a foundational in creating a secure computing environments from hardware components up to the operating systems and application layers. It provides a trusted base that guarantees that integrity and security of system from the moment it powers on. So we can establish a root of trust. Organizations can ensure that their computing devices operate securely and reliably, enforcing a chain of trust throughout the system lifecycle. So now there will be question in your mind. What's the root of trust? A root of trust is a set of functions within a trusted computing module that's always trusted by operating system and application. So this trusted base is responsible for critical operations like verifying a firmware signatures, establishing identity, and performing cryptographic functions. So the root of trust is typically implemented in hardware or in protected layer of firmware, making it resilient to software attacks. So it's very important to understand here what are the components of root of trust. First component root of trust is a secure boot. So secure boot is critical components of root of trust that ensures that device starts in a trusted state. This process involves verifying the digital signatures of operating system and software components before they are allowed to execute. So this verification is based on cryptographic algorithms that ensure the software hasn't been tampered with since its last trusted update. A second is a component hardware-based security. So root of trust relies on hardware to provide a secure environments for cryptographic operations that gonna underpin the trust chain. This often includes the features. So what kind of features we need for hardware-based security? First is a trusted platforms module. It's a secure crypto processor that provides hardware-based security functions. What kind of functions? Like hardware security modules? Uh, it's like devices that manage, process, and store cryptographic keys securely. And also we have a secure enclaves, means protected areas in CPUs like Intel SGS that provide additional security for sensitive data processing. Now we have to understand here a third components of root of trust. This is a cryptographic verification. So it performs cryptographic checks to validate the integrity and authenticity of system software from firmware updates. So this includes checksum and hash functions. It means we're gonna validate the integrity of software, digital signatures, and we're gonna authenticate the source of software because we wanna make sure there's no any kind of change or there's no alteration. And we also can implement root of trust that involves integrating a secure hardware and software practices into the design and architecture of a system key. So what actual steps we need? First, we have to select a secure hardware. It means we ensure the hardware selected for building a system includes a support for secure boot and cryptographic operations. Second, we develop a secure boot process, means designing and implementing a boot process that checks for integrity and authenticity of all the software components before execution. And the third one is enabling cryptographic protection. Means we have to utilize cryptographic mechanisms to protect data and validate software during or after boot. So what kind of benefits of root of trust? So first important benefit we gonna get from the root of trust is enhanced security. It provides a robust defense against rootkits, bootkits, and other low-level malware. Second, it gonna provide the trustworthiness, means ensures that system operates as intended even in the presence of hardware or software attacks. Third is a compliance. It's gonna help in meeting regulatory and compliance requirements that mandate strict security measures, especially in sensitive industries. So let me conclude a root of trust is an essential security concept that provides a secure foundation for all subsequent operations of computing system by uh, anchoring the security mechanisms at the hardware level. The root of trust ensures that the integrity, confidentiality, and authenticity of operating system and applications are maintained throughout the life cycle of device. So as cybersecurity threats continue to evolve, the root of trust will remain a critical component in the design of secure system, ensuring that trust can be reliably established and maintained in increasingly complex computing environments. So I hope you got idea from root of trust. Now we have uh, here a file system encryption. So in the digital age, protecting a sensitive information against unauthorized access is a paramount concern for individuals and organizations alike. File system encryption is a critical security measures that involves encrypting data stored on a disk by operating system. This encryption can be applied through various methods, including a full disk encryption and file-based encryption, each serving to safeguard data by rendering it unreadable without the correct decryption keys. So let me understand the overview of file system encryption. The file system encryption is designed to protect the confidentiality and integrity of data that's stored on computer systems. So it's especially important in scenarios where physical security cannot be guaranteed, such as with the laptops or external hardware drives that can be lost or stolen. So the encryption serves as the last line of defense by ensuring that data remains protected even if a storage medium falls into the wrong hands. Full disk encryption is one of the most comprehensive approach to ensuring or securing data at rest. Full disk encryption works by automatically encrypting every bit of data that goes onto disk and decrypting it as it's read back to the system. So this process is transparent to the user and does not affect the operations of applications. Full disk encryption protects the entire disk, including system files, application files, and user data, along with the empty space on the disk, which may contain uh, many things. So how we have to implement FD? FD means full disk encryption is typically implemented at the hardware level, like self-encrypting drives or software level. If we're gonna implement at a software level, then we can use like a BitLocker for Windows, or we can use like a File Vault for Mac operating system, and we can use DM Crypt for Linux. So key management is also important. So in many systems, keys are stored in a dedicated security modules or trusted platforms to enhance security. File-based encryption gonna offer more granularity than a full disk encryption. With a full disk encryption, individual files or directories are encrypted with potentially different keys. This is gonna allow for more tailored access controls where different users or applications may have access to specific files without needing access to the entire systems. And what are the use cases of the full uh, base encryption? So it's particularly useful in multi-user environments and also essential for systems where files need to be individually secured. It also allows for encrypted files to be securely shared across networks or cloud storage. And also it has benefits of technologies, means a popular implementation of full base encryptions include Microsoft's encryption encryption file systems on Windows and various third-party encryption software that integrates with the file systems. So now the question is, what are the benefits of file system encryption? First benefit is data protections. It means it gonna ensure that data confidentiality and security against unauthorized process and access, especially in the event of theft or loss of physical device. And are gonna help in compliance. It means it helps organizations meet a legal and regulatory requirements regarding data protections such as GDPR, HIPAA, or SOX flexibility. And also, different encryption methods can be applied according to the specific needs and security policies of the organizations. So what kind of challenge and considerations we need to think about that? First, performance overhead. Once we have this, then encryption can introduce a performance overhead, means particularly the full disk encryption, which may impact the system speed. Second concern challenge the key management complexity. It means managing encryption keys, especially in a large or dynamic environments, can be complex and requires robust security practices. And third is a concern is a data recovery, means encrypted data can be difficult or impossible to recover without the correct keys, raising the stakes for key backup and disaster recovery planning. So let me conclude a file system encryption gonna provide essential security for data at rest, shielding it from unauthorized access through robust cryptographic techniques, whether through a full disk encryption or file-based encryption. Implementing these technologies require careful considerations of the balance between security, performance, and manageability. As data breach continues to pose significant risk, file system encryption remains a critical component of a comprehensive data security strategy. So let me stop here right now. We should take a break. After break, we're gonna continue again this lecture. So it's good to stop right now. So I hope you should take a break. After break, we will continue this process again. Okay, all right?
Okay, thank you.
Yeah, take a break, please. Thank you.